Welcome to Introduction to Manufacturing. Today we'll continue talking about electronics manufacturing. And really what we learned is at a very high level that we start with a ingot of material that's derived from sand, and we use processes to get into this ingot. And then from the ingot, we slice it to get the silicon wafers. And then we start the integrated fabrication process on the wafer surface. And from there, we will extract the various chips and then we'll package it. And that's where we've been focusing on this particular lecture today. Is we're going to be talking the later aspects as well. So we talked about in general how integrated circuits are derived from. Silicon is the most widely used semiconductor material. And that's what we use primarily to be able to create the electrical interconnections required on this small flat surface. And we talked about the various applications which everybody's aware here due to the extensive use of these components on electronics. We talked about the levels of integration in microelectronics. They can go from very small integration all the way to the giga scale integration. We talked about a chip, which is what we're talking about here. And this chip can consist of hundreds of thousands of microscopic electronic devices, and they have a particular dimension no more than an inch on a side, but very thin. We talked about that. And we talked about these chips having separate layers of material with different electrical properties that when they're interconnected, they can perform a particular function. From there, we talked about the IC transistor, the integrated circuit transistor, and what we talked about here is a MOSFET. And a MOSFET is a metal oxide semiconductor field effect transistor, and it's a voltage control device. And this acts as a current source to amplify or switch the electrical signals back and forth. And in general, we talked about the silicon substrate, which we have here. You have the silicon dioxide, which is here. You have your P glass here, and then you have your gate. And that's your source and your drain. So those are the kinds of things we need to make an integrated transistor. We then talked about integrated circuit. That's what it looks like. That's a zoom in of an Intel Pentium microprocessor. Very complex, as you can see here, with a lot of different layers here in this circuit. Then we talked about the packaging of ICs, integrated circuits. We talked about using plastics or ceramics because they do provide mechanical protection and environmental protection to the chip. You do have exposed areas that are going to be conducting the electricity to the outside world from the inside the chip. And the big picture there was that you have your chip die here, and then you have your bonds to the LEDs, and then that's your LED frame, and then you have your molded plastic that encloses it to be able to protect the system. We call that a dual inline package. Then we talked about the processing step in the silicon integrated circuit approach. The first one is the silicon processing by itself. We talked about the integrated fabrication process using lithography to be able to define the regions of the wafer surface. They're going to be processed on the wafer surface. And then we talked about the packaging, how the wafer is cut, tested, and we'll be talking a little more today, more detail there. And then here's what we talked about the different steps. You have your pure silicon being formed from a molten state into this ingot. We slice into wafers. Then we fabricate the integrated circuits on this wafer surface, and then we will cut, get the chips. We haven't gotten there yet, but we'll discuss those more today. We talked about the importance of clean rooms in the fabrication process because the various contamination levels can really affect the feature sizes on an integrated circuit. We talked about how the integrated circuit feature size has dropped over time with ear size. And so therefore, airborne particles can now contaminate the processing based on this information. You have a clean room classification here. We talked about the various classes, class 100, class 10, and so forth. And then we talked about silicon processing by itself, which is basically going from the production of electronic grade silicon to crystal growing to shaping the silicon into wafers. And for that, we talked about how the silicon is derived from sand, and then we apply various processes like HCI, and then we'll form this product here. We'll then combine with this hydrogen, which will separate the silicon into nearly 100% silicon. And then from there, we use a process called crystal growing, which we want extra high purity. We want to be able to grow it using something called a Socrates process. And in this case, we can get a single crystal bowl from a pool of molten silicon. And this single crystal approach allows you to derive certain properties in particular directions. And here you can see that. Here I have the rotation device. Here you have your seed crystal, your molten silicon, and then your crucible here, and then the vacuum pump. And all that is allowing the amount of crystal here to grow into the silicon bowl. And then from there, you can now start with the ingot bowl preparation process. This includes being able to clean it. You want to ground the surface. You want to put a marker here so you know which side is the crystal orientation. And then you're going to apply more cleaning. You'll have then this wafer being cut using a diamond abrasive cutting edge approach. And then each wafer will now be prepared. And how you do that, you contour grind the edges of that wafer. You'll chemically etch the wafer to remove any surface damage. You'll polish it, and then you'll chemically clean it again to remove any residues and organic films. And there's a YouTube video that I suggested you watch that goes into that. Then we talked about the integrated fabrication process, circuit fabrication process onto the wafer. That's what we discussed next. And lithography is what we talked about, that allows you to be able to imprint a geometric pattern that represents the circuit design information. You transfer that into the lithography, into the wafer using lithography. And that's what's going to allow you to create the interconnections in the circuit design. And here we talked about how we can use ultraviolet, which is a different class of lighting compared to visible light. And then this is what we're going to be using is photolithography. And so you can process it using that approach. And we're going to use a mask, a photolithography mask. Basically, it's going to use a thin glass particularly. And that glass is going to have some amounts of opaque substance, which we are calling mask in certain areas. That's what's going to form the pattern. The mask itself is fabricated with lithography. So the mask itself is using the very same approach that we're going to be using to create a pattern, which is going to be based on the circuit design data. And that's going to be passed over onto the wafer. So we talked about that quite a bit. We talked about photoresist as part of the process, which is to use sensitive approaches to be able to pass the information that you want onto the wafer. And then here, the general approach was always about the same, where you have your mask, your resist, your silicon, and your silicon oxide here, the dioxide. And here you have your lens and your ultraviolet light source. And what we're trying to do here is we're trying to press the mask onto the resist coating during this exposure. And that's what's going to cause the contact printing of that approach. This provides a high resolution. We talked about projection printing. In this case, it's a non-contact technique, which is preferred because the mask will not wear over time. You also obtain a very high resolution. And then we talked about the processing sequence approach, where you have your silicon here, and then you're going to have a surface of the silicon wafer, which will be oxidized to form this layer. And then we're going to remove this oxide, silicon oxide, from certain area. And that's going to help us create the pattern needed. Then we have your resist that's going to be applied, the photoresist. So this is where you're going to have, first you're going to have a wafer properly cleaned to let the adhesion work of that resist. And then you're going to apply a liquid resist into this wafer, and you'll spin it to get a nice uniform coating. You can see that here in the bottom left, there's a YouTube video also you can watch. And then you can do a soft bake. This soft bake is going to remove the solvents, make sure that the adhesion and the hardened resist, and then you're going to then apply UV radiation onto your mask material, which is not going to be, you're going to align these obviously relative to the wafer, and then you're going to expose that light onto the resist. And then we talked about how the wafer now is going to be immersed in the developing solution here, and then you're going to have a negative resist to get the unexposed area dissolved. In this area, you can see that this mask here with this protrusion has now caused this area here to be removed. And then we're going to do a hard bake to remove any volatiles and increase adhesion. And then we're going to do an etching solution to remove a silicon oxide layer at some areas where the resist was removed. And then you'll do a strip resist here, which is to remove any extra material by stripping using liquid or plasma etching, as we discussed. And then we talked about a layer fabrication process where you can fabricate one at a time. Each layer requires a separate mask. We talked about this. And then we talked about 5 approaches to do the layering: thermal oxidation, chemical vapor deposition, diffusion and ion implantation. And then we talked about last 2 steps here called metallization and processes, and then the etching processes. So 5 processes needed to get there. And we talked about quite a bit about this. The first one talked about how to be able to do the thermal oxidation process, which exposes the silicon wafer to an oxidized atmosphere, so that you can form that layer of material we discussed. So you can go from here to this layer of material we discussed. So that's caused this before oxidation, and then this after thermal oxidation. And then from there, you have the functions of the silicon dioxide. We know that silicon dioxide is an insulator compared to silicon, which is a semiconductor. So that's actually very nice because the silicon is what they want conducting, and we're going to use silicon oxide as an insulator. So I'm creating pathways that I want in an electrical circuit. So we use this mask to prevent diffusion or ion implantation, and it can be used to isolate devices in a circuit, as we discussed. You can also create electrical insulation between levels in multi-level metallization systems. There's also alternative processes for adding silicon oxide, and so that's very helpful. You can do that by using chemical vapor deposition is one approach that people have used. We can also introduce impurities into silicon, and we do that on purpose. We call this doping, and we do that to be able to dial in what we want to have in terms of insulation. There's 2 approaches we discussed: the thermal diffusion and ion implantation in the very last lecture. We discussed the thermal diffusion process, which is number 1. And then we talked about ion implantation. Both are trying to achieve the adding impurities into the silicon surface. And again, we're doing that to alter the electrical properties so we can get the properties we want in terms of the conductivity. Then we talked about metallization process, which is to combine the various thin film deposition technologies with photolithography to form the patterns that we need in the conductive material. And so we talked about connecting these paths, these conduction pathways, and then connecting the chip to external circuits. That's really what we're after. So the metallization materials we talked about last time was aluminum, and other materials have been used in the past. And the 3 processes for metallization was physical vapor deposition, chemical vapor deposition, and electroplating. All those were covered last time. And then we talked about etching, which is an important process. And there's 2 approaches used. The etching is used to remove the material, and then we're trying to remove it in the areas of unwanted material. And how we achieve that, we already discussed that a few times, but we achieve this by masking surface areas. And then there's 2 categories. There's the wet chemical etching and dry plasma etching. We talked about that before. The wet chemical etching is a chemical etching reaction that's isotropic, and then the dry chemical plasma etching uses ionized gas to be able to etch the material. And then we're going to now talk about process integration in an integrated circuit fabrication process. And just to remind you that MOS is a transistor, and M stands for metal, O stands for oxide, and S stands for semiconductor. So here's what we're showing, and we already showed the different parts, what they mean. But now we're going to talk about the process integration of these integrated circuits. So the lecture now begins for this part 2. Part 1 was a review because it can be quite overwhelming. This is not an easy manufacturing process, but that's why it's so important to talk about it, because it's not talked about very much in a lot of manufacturing courses. And in many courses, these consider additional extra material, but I think it's very important that we kind of learn about this in extensive detail. So in number 1 here, what you see is how I basically fabricate this NMOS, right? Metal oxide semiconductor. So we're going to deposit a silicon nitride type on the silicon substrate. We're going to have it patterned. So you're going to use selectively etched photolithography to be able to put that deposit in the areas that you want. And then the silicon oxide will be grown by thermal oxidation, as you can see here on the edges of that in the unmasked regions. So here I have this material, but I'm going to grow these areas with thermal oxidation. And remember that this SiO2, the dioxide here, this material is not as conductive as silicon. In number three, when we remove the mask that was there, which is this Si3N4 material, and again, that was put in there as a pattern that we can remove. And then we will do additional amount of silicon oxide again by thermal oxidation. We'll grow a little more to add that extra layer. And then we're going to go into a polycrystalline silicon that's deposited by the chemical vapor deposition process. And we'll dope this with N plus ion implantation. So this is going to be done with a chemical vapor deposition process. And so then we're going to pattern it with a gate electrode. That's what you see here. And then we're going to apply a source and drain to form the N plus substrate. So that's what you see here in red. And then we're going to apply a P-glass onto the surface for protection. So those are the kinds of steps needed for the integrated circuit fabrication process. And now we have the device that we call, and you may have heard of this, but it's called the metal oxide semiconductor field effect transistor. That's why it's called MOSFET. The real device is a lot more complicated than what I showed, but again, this is to give you an overview. And you need millions of these devices to be able to make a chip. Hundreds of dies are made on a wafer, and there's dozens of wafers are processed in a batch. So it's a lot of wafers being processed, a lot of chips being processed here, and a lot of devices in the millions are being made. You can see here the system on the right being showed, the MOSFET here, and the complexity of it with all the layers shown with different gates. The final processing step on the integrated circuit packaging is to take the wafer, cut it to get your chip, and the chip will then be integrated in this packaging, which we call DIP. So what are the manufacturing issues with the integrated circuit packaging? As you saw, these are very complex process. There's going to be a lot of issues. So we need to separate the chip from the wafer. This process is called the chip separation process. We cut the wafer into individual chips. We call this singulation. This process of chip separation is called singulation. We'll connect it to the package. So we're going to connect this chip onto the package. We'll encapsulate the chip, and then we'll do circuit testing. So what are the factors that drive the package design? Is really the number of inputs and output terminals required for the integrated circuit, the materials used in the integrated circuit, and package styles. For the input and output terminals, the basic issue there is how you can create the appropriate electrical signals and how you're going to connect them to the outside. That's really the question. And as the number of these integrated circuit increases, you also need to increase the number of input and output terminals. So the problem also has been aggravated over time because the sizes of these chips have decreased, the integrated circuits. And so that increases the number of devices in the circuits, which means you may need some other way of going about this. So the packaging materials used, we talked about this before, but these more going a little bit deeper. Ceramic is one of them. The advantage there, it provides a hermetic seal. Disadvantage there is provides poor dimensional control. We also use plastics that are not hermetically sealed, but cost a lot lower, and is generally used for mass production of integrated circuits, where you don't need the high reliability. There's two basic types of integrated circuit packaging, and for assembling integrated circuit packaging, just printed circuit board, you have two kinds. One is called the pinhole technology, where you have these LEDs that go through this material here and it's soldered on the other side. So that's what this one is about. The other kind is called the surface mount technology, where in this case, you're attaching it to the surface of the board. And then you have major integrated circuit package styles. You have the dual inline package, the square package, the pin grid array, and some of them may be either the top or the bottom. So you either have a PI system or SMT system. Again, this top one is going through the material and then soldered on the sides through the polymer. in this case, is soldered on the top. And then again, three types are used. So if I go to a dual inlay package, it's very common. Usually you can do both the pin through hole or the surface mount configurations. Usually 16 terminals, as you can see here. The square packaging, in this case, you have array where you have in and inputs and outputs on each side, and they tend to be multiples of 4. You then have the pin grid array system, tends to be a pin through hole, but not always. In this case, you have the bottom surface fully occupied by pins, and then it's an N by N type, so it's a square. And the center doesn't have the pins because that's the region where the chip is at. So you can see the opposite side here on the left side. The ball grid approach and the line grid approach are shown on the left and right sides. They're all used. So now what I'm going to talk about are what are the processing steps in the integrated packaging approach. The first one is called the wafer testing. So I have my wafer, I have to test it. Then I have the singulation. Then I'm going to have the die bonding, which is the attachment process. Then I'm going to have the wire bonding, the package sealing, and the final testing. And hopefully these are all making sense to you. Okay. So for the wafer testing, we should talk about, we'll talk about more about the wafer testing. So the testing is accomplished by a computer controlled equipment, which we call needle, that matches connecting pads on the chip. Many of these tests are performed while the integrated circuits are still in the wafer before separation. And the probes are going to be used, are contact pads that are typically used. And the tests are carried out to indicate short circuits and other faults. The chips that are failed are marked with a little dot, with a ink dot, and these defects will not be packaged. The ones that are acceptable are typically known good die, KGD. So you'll hear quite a bit about that. Chip separation, the wafer will be cut into individual chips using a diamond saw, as we talked about earlier. The wafer is attached basically to an adhesive tape mounted on a frame. The adhesive tape will hold individual chips as you're getting the cutting done, so you don't lose them. And the frame is there for convenience for handling the chips, because otherwise there'll be a mess. Now the chips that had this red dot that were marked, we're going to discard those. And now we have the die bonding. So these are automated handling system that allows you to pick the separated chips from the tape frame. So I'm going to remove them from the tape frame that we talked about, right? We were using this tape here to keep all the individual chips in place during and after the sawing. So I'm going to have that process there, and I'm doing it so I don't lose them. So I'll separate it from the tape and place them for die bonding. So there's two approaches that people use for die bonding. If it's ceramic packages, we use called the eutectic die bonding, and if it's for plastic packages, epoxy die bonding. So then you have the wire connections. After the die here is bonded onto the package that you see here, that's a substrate packaging material, which can be a polymer, for example. You're going to have the electrical connection being created between this contact pad from the chip to the lead frame. And this wire can be, this copper, the lead frame, and this wire can be aluminum or some other material. And you can see a picture here on the bottom right of a realistic one. And then here, you can see the blue is this right here, the chip die. And then the leads is this wiring. And then here, this in orange is what you see here in dark brown. And sorry for the inconsistency. So now we're going to package the integrated circuit chip. So here you can see the cutaway of that. We already showed you this before. So then we're going to do final testing. So once we integrate everything together, we have to do a final test. And the idea is to determine whether a unit has been damaged during this packaging, because everything is so sensitive, as we saw. And we have to measure the performance characteristics of each device. If these systems will fly on a spacecraft or some launch vehicle, we do a lot of vibration testing to make sure that a lot of this wiring does not come apart. So what are the yields in integrated processing? There's so many processes involved and hundreds of distinct operations that a mistake can be made. So at each step, there's something that can go wrong, and that can then result in the loss of the wafer or portions of the chips not being useful. And so the reality is that there's a lot of issues with this processing. It's very manufacturing sensitive. You can see here when I tried to create the bowl relative to the electronic grade silicon, 50% of it is good. When I slice it, only 50% of that is good. When I have a wafer yield, after that, whatever survives out of this, 70% is good. Then from there, the testing only passes, not everything passes, less than 10%. And then the final yielding is after the packaging, after you get to this point, is 90% to 95% pass. So you can see here the difficulties of being able to produce at mass. Here you can see the probability model of predicting good yield. The given typical values I showed before show you that what I get at the end is quite low. So the yield can be quite low if you multiply 0.5 times 0.7 times either 0.1 or 0.9, depending upon what's going on, and then times 0.9. It's going to be very small, less than 10%. So the key, what this tells us is that there's a lot of room for improvement in this area of expertise. And the key successful integration circuit fabrication process is that if you want to be profitable, you have to achieve very high concentration of processes that are done as close as perfect as possible. How do I do that? The purest possible materials, the latest equipment technologies, good process controls, maintaining a very clean room condition, and very efficient and effective inspection and testing procedures. Because of this, if any of those things are bad, this is going to produce a low yield. As you can see, everything's multiplied here. Any of this is impacts the overall yield. So now I'm going to dive into electronics assembly and packaging. So what we talked about so far is how I create this integral circuit that has been packaged. But now this needs to be put into printed circuit boards and so forth. So we need to talk about how to get to this stage, how we do the other assembly and integration processes. So first, we need to talk about the packaging hierarchy. Level 0 is a chip die level where you have, as we discussed before, your transistors. Then you have your package chip, which is a level 1. And this package provides interconnections. We call this dual inline package. Then you have your level 2, where these package chip are interconnected in a circuit board with other components. And then you have level 3 there, which is the circuit board here in level 2 is put into a rack, as you can see here. And you have your board packaging. And then number 4, you have your wiring and cabling connections in the actual cabinet that provides the capabilities needed for whatever was required. So those are the 4 levels. It's actually 5 levels, but goes from 0 to 4. The printed circuit board here is one or more thin sheets of insulated materials with copper conducting paths on both or one or both surfaces, so it can be either or both surfaces, that interconnect the components attached to the board. And that's what we talked about here in level 2. That's what we're talking about there. So these printed circuit boards are used in packaged electronic systems to hold and electronically interconnect components. These are the standard building blocks that virtually all electronic systems contain the packaged integrated circuits. So this is the building blocks of what we need. So what are the insulating materials used in industry? They can go from epoxy, polyamides, e-glass. You can have substrate layer thickness from 0.8 millimeters to 3.2 millimeters. You can have a copper foil thickness of 0.04 millimeters. And the principal types is, like I said before, single-sided board where copper foil is used on one side, the double-sided board where copper foil is used on both sides, and the multi-layer board where you have alternating layers of conducting foil and insulation. And 4 layers is the most you'll ever see, typically, for most configuration. And here you can see the pictures of it. So here you can see the insulating substrate. Here's the copper foil. For the second kind, the double-sided, you have on both sides. And here you can see the copper foil in 4 locations. So the overview on the printed circuit board industry here is what we're going to be talking about. So first we're going to talk about the production of the copper foil. This production here consists of continuously electroforming it by using a rotating smooth metal drum that's partially submerged in this electrolytic bath that contains copper ions. The drum tends to be a cathode in the circuit, which causes the copper to plate onto the surface. So that's what we're talking about there. As the drum rotates out of the bath, the thin copper foil is peeled from the surface. And this process is very ideal because you can produce very thin copper foil. So electroforming again is what we're using here to create the copper foil that's very thin. Now, when you look at the complete board, it consists of glass fabric, reinforced thermoset panels. Now you're ready for the circuit fabricator. This is usually produced in large standard widths designed to match the board handling system. So now I have to create holes into the PCB. So the way you make that, you drill it or punch it. You want to make sure that things are clean. The drilling holes is cleaner, but punching is faster. Most holes in printed circuit boards are drilled. A stack of 3 or 4 panels may be drilled together using a CNC drill. For high production jobs, you have a multiple spindle drill that's sometimes used. So, to create a circuit pattern imaging, you're going to still use the same approach, screen printing and photolithography. So both methods are used, and they use a resist coating like we discussed before on the copper foil, and then that's going to help you determine where you're going to etch the copper so you can create the tracks and the connections. Again, resist is used again here. And now you have your circuit pattern etching, where you have the covered areas are the circuit tracks and lands, the uncovered areas are the open regions between them, and the etching is attacking everywhere where the resist is not. So the etching is really removing the copper cladding in those unprotected regions where the resist is not, right? We're going to use resist to do that. And so now we're transforming the solid copper here to create the interconnections required. So you have to remove basically these blues resist after you're done. So then you have your plating. Plating is needed on whole surfaces too, if you're going to have conductive paths on both sides. So there's 2 approaches that people use to make that happen. 2 of them is called the electroplating approach, which is a higher deposition rate but for coated surfaces, and then electroless plating, which is lower but does not require a conductive surface. So you have features of a double-sided printed circuit board. And so here you have your insertion hole, your via hole, and your tracks and your lands. So that's going to allow you to show various features. It's going to allow you to be able to create the connections that you need through the copper. Because remember, this brown here is your insulating substrate. So you're trying to create your tracks. So now I have a printed circuit board assembly. The electronic components are now going to be ready to be put together. That's going to include integrated circuits, resistors, capacitors, and also fasteners and heat sinks. They're all going to be mounted on the printed circuit board. That's what we call the level 2 in electronic packaging. Let me show you where we were at in the levels. That's level 2 here. That's what we're talking about there. And so we talked about pinhole or surface mount technology. So to process the printed circuit board assembly, it consists of the component insertion into the holes of the circuit board, soldering the leads onto the places in the hole, cleaning, testing, and rework. For component insertion, that's the first step here. The single board may be popular with hundreds of these components. We talked about that earlier. Today, a lot of these insertions are done automatically. A very small portion is done by hand. That's very non-standard, but it can be accommodated with automatic machines. Here you have the automatic component insertion. Electronic components are inserted into the printed circuit board. You also have, now when I look at the 2 or 3 basic types using an automatic insertion machines, is an axial lead, which I show here. That's your body, and that's your lead. And this can be bent for insertion. And then B, your radial lead. That's your body, and that's your lead. So now going back here, the second step is soldering. We need to solder those into the holes. There's 2 approaches used, the wave soldering and hand soldering. The wave soldering uses a mechanized technique. So you're gonna only be able to do it on the underside of the board, and then you're gonna use capillary action and the force of wave that causes the liquid solder to flow onto the clearances. That's how it works. All solder joints are made in a single pass. So then we have wave soldering, molten solder wets and sticks to the metal, but not the plastic surfaces. So here's your molten solder. Here's your wave soldering being pushed, and then here's your components being the ones I want to solder, right? These are my different components. And so this approach is going to stick to the metal, but not to the plastic. And that's what's causing this to work very nicely. We call it wave soldering. And there's a wave soldering video on YouTube, so check it out later when you can. But then you have your hand soldering. That requires very skilled operation with a soldering iron. And I've done this. It's very hard to do. It's slow because each solder joint has to be done one at a time. It's generally used for small lot production and rework. There's also human error issues that can result in quality problems and sometimes can be used after wave soldering to add delicate components that could be damaged. So these not used everywhere. These only used where you cannot use wave soldering. And this can introduce error because the soldering can have voids. The next step is cleaning, testing, and rework. And I will say cleaning is very important because you have to clean it from all the solvents, all the flux, all the grease, salt, and dirt. By the way, this tends to be one of the reasons why you don't get a good product, is because people forget to clean and it needs to be cleaned very good. You have visual inspection to detect missing or damaged components, also functional testing to ensure proper circuit operation. And then you have the rework, manual repair of defects found in inspection and or testing. So now we go to surface mount technology. That's an assembly method where you're gonna mount it on the surface as an approach that's going to be used in cases where there's limitations with pin in hole approaches. So this works if you can only apply components on only one side of the board and you have relatively large center to center distances between the lead pins. So that's where that's useful. The advantage of surface mount technology is that you can have components closer together. It increases the packaging density because now you can put stuff on the top but also on the bottom. While here, if I go through, that's an issue. I can't use the other side in an easy way. The components can be then attached on both sides, increasing the real estate really, and you eliminate any drilling, which is very nice because now you have less foreign object debris. I have less cleaning to have to do, and you still have to interconnect layers, but less holes. The correct positioning of the component on a printed circuit board is very important and is done quite a bit. It needs to be done carefully, obviously, and they can use tape or other ways to figure out how to do that. Now, how we put these components on, we can use bonding or wave soldering. We can also do solder pasting and reflow soldering. So those are two placement techniques people use. So here you can see number one, where I have my adhesive, I have the lens and the track. So here's my board here. I can use adhesive that's applied on the board. So I'm applying it here, and then these where the components will be placed. And then here you can see the component being placed successfully in number two. And then the adhesive is cured now with temperature. And then also you have solder joints that are made by wave soldering to create more paths, electrical pathways. And that's between the metallized and the component layer. The other approach I talked about to be able to achieve the surface mount technology is called the solder paste and reflow soldering. Number one, here we're going to apply the solder paste. In number two, we're going to put the component lead. And then three, we're going to apply some bake. And then four, we're going to apply solder reflow to be able to create a nicer pathway. After solder paste application, the components are placed on the board by insertion machines. You have a low temperature baking operation that's performed to dry the flux binder. And then you're going to do a reflow process. And that's done to form a higher quality mechanical and electrical joint between the LEDs and the circuit lands. So now I'm going to go ahead and start bringing this printed circuit board to the back planes, into the racks and cabinets. And really the performance of any electronic system depends on how I'm able to link these things together. So that's going to, when I talk about connector technology, I'm looking at third and fourth levels of electronic packaging. Going back to look at the list here that we had shown, we're talking about number 3 and 4 now. So the circuit board on the rack and then the wiring and cabling connections. So hopefully that's making sense to you all. So these are very important steps here. So far we looked at, we assume the integrated circuit chip is packaged into integrated circuit package. The inter-circuit package is assembled in a printed circuit board. But for small electronic systems like smartphones, the lines between inter-circuit packaging and printed circuit boards is kind of blurred. But many concepts and names have appeared there when you're looking at smartphones. We need to really understand other things as well. And that includes through silicon via and fan-out wafer level packaging, which will not be covered in this course, but I want to raise that to your attention. With that said, I want to thank you for your attention.